zip227 for the issuance aspect, and zip230 for the changes to the transaction format. We had our main pull request, which was PR680, merged some months ago, and these zips are now available on the Zcash zips website. Of course, they are still in draft mode, and we have made some small updates post then. These updates will be added to a new PR in the zips repository. However, the design is essentially stabilized with no major changes expected. We made a pass through the Orchard ZSA circuit we had implemented last year, and we have done various optimizations since then. The goal of optimizations is to reduce the proof size, reduce the time to create the proofs, and reduce the time to verify the proofs. There are often trade-offs between achieving all these, and so the aim is to strike a good balance between all of them. We'll now take a look at the result of optimizations we performed in the ZSA circuit. Note that since we now deal with multiple types of assets, there are various different places where we have additional or different checks as compared to the Orchard circuit. So I'm not a fan of having a lot of data on slides, but there really is no better way to talk about optimization, is there? So I won't ask you to really look at the numbers, and I'll try and give a gist of what to look at in this table. First off, what do these rows represent? The first row is the details of the Orchard circuit that was already deployed in NU5. We began by just getting all these additional checks in to create a ZSA circuit that was complete and functional. This is the second row, which is before optimization in that table. The final row is the result of our optimization, so after optimizations. So in the circuit before optimization, you'll notice that the number of rows went to 2207, which is above 2048, which is 2 to the power 11. This was one part of the reason for the jumps in the proof generation and verification times that we see there. So the optimizations we performed were able to bring down the number of rows in the circuit significantly. And therefore, we now have pretty reasonable increases in the proof size, proof generation, and proof verification time values as compared to the Orchard circuit. We'll now give a very short summary of the optimizations that helped with this improvement. One optimization was regarding the Synsomia hash that is used both in the ZEC and the ZSA cases. There is a portion of the hash that is computed in the same manner for both cases, followed by a diversion towards the end of the computation. We updated the circuit to do the common part of the computation in the same way for both, with a divergence at the point where it was necessary. This was more efficient than having the entire hash portion of the circuit repeated twice. The other optimization we performed was the addition of some rows and an additional column in order to be able to perform shorter range checks more efficiently, which is required within the ZSA circuit. So that's the update on the ZSA circuit. The Orchard ZSA protocol, however, extends beyond the circuit too, so we'll now take a look at that. At a high level, our status is that the updates that we have made to the Orchard crate to make it support the Orchard ZSA protocol are stable and working. They are based over Orchard 0.8, which is the latest version of Orchard. You might notice that last year we were based on Orchard 0.5. So clearly, we are working towards a moving target, and it's often the case that the updates that were made to Orchard upstream end up breaking our code and require revisits to multiple areas to fix things. However, this rebasing is an important and non-trivial part of keeping our code and pull requests ready for merging whenever the maintainers begin that process, which is why we are keen on staying on top of this. One of the other crates where there has been significant ZSA-related change is the Zcash note encryption crate. The ZSA protocol makes a change to the note structure that lengthens the plaintext being encrypted. The ECC roadmap for NU6.2 includes a generalization of the note encryption design to prepare for this change. We have recently submitted a pull request to the Zcash note encryption crate, that's PR2. We are expecting review of that to begin soon, and we'll be glad to see it merging in the near future. Backward compatibility is another piece of the puzzle that's been on our plate for the last many months. We need the ZSA protocol to work seamlessly with Orchard and Sapling and share the Orchard anonymity pool at the same time. The work in this backward compatibility area does the task of allowing the software to be able to read both older notes along with the newer notes and things like that, for example. We'll dive a little bit more into the specifics now. We'll start with the Zcash note encryption crate. So, like I mentioned, the vanilla Orchard note structure is 564 bytes long. And in the Orchard ZSA note, we have to now include details of the asset base, whether it is native Zec or otherwise some custom asset. That has to be included in every note. This adds 32 bytes to the note structure, which makes the Orchard ZSA note a total of 596 bytes. The work we did in the PR2 that I mentioned earlier, it generalizes the note encryption code to allow for the encryption of notes of both these lengths in elegant and efficient ways. The next bit is about the Orchard protocol and the changes that we make on the addition of ZSA functionality. We use Orchard bundle to refer to the part of the transaction that encodes the Orchard pool related information. So the original vanilla Orchard bundle uses the vanilla Orchard notes, which we saw were 564 bytes long, and the zero knowledge proofs that are generated for verification by consensus are generated as per the Orchard circuit. So the new Orchard ZSA bundle, on the other hand, uses the longer Orchard ZSA notes. The zero knowledge proofs are also generated using a different circuit, specifically the Orchard ZSA circuit that I described as optimizing earlier. The circuit performs the various additional checks that I mentioned earlier. We have completed this work, and both bundles are now supported in our pull request to the Orchard crate. This work has been successfully tested against the Python reference implementation for vanilla Orchard, as well as a reference implementation we made for the ZSA protocol. In addition to the expanded Orchard ZSA bundle, the ZSA protocol introduces an additional bundle for the issuance part of the protocol. This issuance bundle contains all the fields of the transaction that are present when assets are being issued. The structure of the bundle looks basically like this. We have issuance actions in these transactions using a terminology analogous to Orchard actions. We'll look a little bit more into how they are structured really soon, so stay tuned. We also have an issuance validating key, IK, which is a public key for the Schnorr signature scheme that is unique for each issuer. The issuer signs the issuance details into an issuance authorization signature, which serves to validate that issuance was done by the party with the authority to issue those assets. As promised, we'll head back now to the structure of the issue action. The issue action contains an asset description string, which is an up to 512 byte description of the asset that is chosen by the issuer. The issue action also contains a number of issue notes with the details of how much of the asset is going to whom. So as we mentioned a bit earlier in the talk, the issuance procedure is transparent, for which reason the notes are unencrypted and it is public as to how much has been issued and to which address. The last piece of information inside an issue action is the finalize flag. This is used to signal when the issuance of an asset has been completed. Whenever an issue action is spotted, the consensus will involve a check on whether the asset has been finalized previously, with a rejection of the transaction if there is an attempt to issue more assets after the asset has been finalized. So the part of the Zcash code base that we turn to now is the Libra Zcash crate. This contains much of the supporting code that generates transactions and does work on the back end and just basically makes a lot of Zcash tick. Our work on this crate adds support for V6 transactions as specified in zip 230, which is, as we saw, the zip that describes the V6 transaction format. These changes include the data structures for the additional and changed components, and also updated computations for the transaction identity and the sig hash. You might recall that issuance bundles contain unencrypted notes since the issuance process is transparent. Therefore, we have also added support for note serialization in the issuance bundle. Next, we'll consider Zebra, which is the Zcash node that we are going to be using for ZSAs. Here too, we have added support for handling version 6 transactions according to ZIP 230. Beyond the ability to handle V6 transactions, we also have node consensus code that can handle the changes that come in with V6 transactions and the ZSA protocol. However, one sticking point was that when while Zebra performs the consensus checking and transaction handling, it does not generate transactions. So we needed the ability to be able to create transactions so that we could test our changes and additions. We therefore made a tool to generate these transactions. We should highlight that this tool is just for testing purposes. We first built the tool for V5 transactions, that is for vanilla Orchard. We then will have the functionality to create V6 transactions, and that includes both the issuance and transfer of Zcash shielded assets. We encourage you to check this tool out. It's an independent repository on GitHub, Zcash-dx-tool, and it contains a Docker that does the setup of everything, begins running Zebra, and then does a set of tests. Of course, you'll be able to go in and tweak the code and change the tests if you want to try other things out. So I'd like to see all of y'all play with it and see how it goes. So this is the one-slide summary of what we covered so far. We did zips, we did the circuit, and we looked at the various code repositories we've been modifying to bring ZSAs out to all of you. We have also begun the work for instantiating a testnet for ZSAs. First, we started local. We ran Zebra locally. We used the Zcash transaction tool that we just described. Then we moved to the cloud. We have run Zebra on an AWS ECS instance using Terraform to build the infrastructure. And we have also connected that with the Zcash transaction tool and run the tests. So this is early stages. We have not tested this out with the ZSA features and with issuance and so on. We have, however, understood how to get everything running on the testnet. So that should be good for when we are ready to test the pieces all together. So where do we stand now? We have started talking to the Zcash ecosystem security lead, which is least authority, about doing an audit of the protocol as we get around to completing the last bits of the puzzle. There are also others like Geometry who had expressed availability to do an audit. So the more external eyes on our work, the better it bodes for security. And we are happy to support whichever audits are planned when they happen. We also have the fees portion that could benefit from some more discussion. As it stands, we have the same fee structure as in the proportional transfer fee mechanism. The prices are per byte. We'd love to hear more consensus on this part so that we can get this finalized as well. We are also in the process of streamlining the gadgets that are in the Halo 2 repository. This is for generating the zero knowledge proofs, the Halo 2. Like we mentioned earlier in the Orchard case, we are keeping abreast of the changes that are happening on all the repositories and making sure that our work builds correctly on top of latest versions. With that, we are now ready to move to asset swaps. But before that, we could probably take some questions if there are any. So yeah, I see there's a question, which is there a mechanism to preemptively set the maximum issuance when issuance begins? Or is issuance only terminated when the finalized flag is set? If it's the latter, what prevents an issuer from exceeding promised bounds by delaying final issuance?
So there is no mechanism to set a limit in advance, and only once the finalization flag been published to the blockchain, it is really finalized. I'm not sure that this is a real limitation, because if an issuer wants to guarantee some kind of some amount which is final, he can just issue the entire thing and keep finalize this asset and keep whatever is not immediately distributed in some kind of treasury. So the process is transparent, and we currently don't see it as a limitation.
Yeah, basically, since the issuance is transparent, it will be visible later. So it's not that, I mean, it's the reputation of the issuer that's on the line in that case. So the next question is, does the ZSA issuer have any way to track assets and transactions once owners have included the ZSAs in shielded transactions? It's basically no, because it's shielded. So we have the privacy just as in Zcash right now for Zec. Does Gedit have plans to add functionality for issuance and transaction creation to the Zcash primitives transaction builder?
So everything is added as part of transaction V6. And of course, the builder structure remains the same as with Orchard. So you build V6 transactions in the same way that you would build V5 transactions, just with a different set of parameters. So yeah, it's going to be part of the transaction builder.
Is the currently implemented functionality feature flagged in such a fashion that it can be merged prior to inclusion in a network upgrade?
So for Zebra, we did put the extra effort to include feature flags for the Zebra crate and for the Zebra code base. But for Orchard, it is currently not feature flagged because it is tightly coupled with the existing Orchard implementation. And I think to feature flag the Orchard/Orchard ZSA crate is a significant effort. I think we're going to review everything in one go, Orchard and Orchard ZSA together, and we're not going to feature flag Orchard. As with Zebra, yeah, it is feature flag.
So I think that's it for the questions for now. So we can continue on with the next part of our talk, which is asset swaps. So yeah, the main reason for Zcash shielded asset swaps is to enable any user to be able to exchange assets with other users in a peer-to-peer manner. That is, we want them to be able to perform these transactions without having to trust a third party or even the party they are swapping assets with. This allows for increasing decentralization over the network by reducing the need for trust in the users. The status of this effort is that so far we have prepared a new zip, which has been assigned number 228. This zip contains the specification of our design for the swaps protocol in the form of changes that are required over the ZSA protocol. We are looking forward to reviews and comments on this protocol so that we can get some external feedback while we move towards implementation. This will also reduce the chance of double effort that might occur if design changes are suggested after implementation is well underway. I'd like to now take some time to go over the main properties of our design, after which I'll go into the design a bit more at a high level. One of the key properties we are aiming for is for users to remain the owners of their asset until the swap occurs. Doing things like transferring the asset to some third party and so on requires additional levels of trust, and that could open vectors for attack, which we'd like to avoid. So instead, in our design, you own your assets until the point the completed swap transaction is on the blockchain, at which point it is a transaction that shows you sent your assets and received the assets you want. The protocol basically works by having someone take two pieces of a transaction that match and combine them together into a complete transaction and put that on the blockchain. The simple use case is that the party doing this matching is one of the two users itself. But our design is flexible enough to also allow it to be done by some third party or third party service. In either case, the protocol is secure and does not need any party to deposit their funds anywhere ahead of time, like we mentioned. The party that does the matching will know the values of the assets being swapped. The other nice thing of the protocol is that it builds on top of the ZSA protocol in a way that tries to maximize the use of the tools and security technology that has been developed for ZSAs and for Orchard. In fact, our design at present requires no new changes to be made to the circuit, which means no additions to proof size, proof generation, and proof verification times. We'll now dive a little bit more deeply into the design. There are two main pieces here, the swap order and the swap bundle. So when a party wants to swap some asset for some other asset, they create a swap order that contains the information of the trade they would like to perform. For example, someone may want to get 3 tokens of asset A by giving 2 tokens of asset B. That's represented in the top left figure in my pictorial description. Different parties will have different desired tokens that they are exchanging for other different tokens. These swap orders that these parties create do not go on the blockchain. They are communicated off-chain by external mechanisms. If you look at the orders, you will see that the person on the top left has an order that matches the order of the person at the bottom. Coincidentally, they also happen to be dressed as per the ZconV color scheme, so that's nice. These two swap orders can then be matched, which leads us to our next piece of the design, the swap bundle. The swap bundle is the result of the combination of 2 matching swap orders. It is this swap bundle that forms a complete transaction, which can then be added to the blockchain, and that completes the swap between the 2 parties. So we can now go under the hood a little bit, starting with the swap order. For the sake of ease of understanding, I want to simplify this a bit so that I can share the core of the idea without too much of the nitty-gritties. If people are interested in the nitty-gritties, I do encourage you to look at our specification in ZIP 228 and talk to us either during the conference or outside of it. We are always happy to discuss. I had mentioned earlier that the swap order is where the party fills in the information regarding their side of the trade. So these are basically 2 pieces. The proposed input, which is what the party wants to send to someone who matches their order, and the desired output, which is what the party wants to receive at the end of the transaction. The pieces of information needed are the identifier of the specific asset and the value specifying how much of the asset is being exchanged for both of these pieces. For the specific exchange the party has in mind, that will be the input will be 2 tokens of asset B and the output will be 3 tokens of asset A. Further, the swap order will contain the sum of the randomness of commitments from these pieces, which will be used for combining the orders later, so you can keep that in mind. The next part of the swap order is the relevant action group descriptions. These are similar to action descriptions that we have for transactions in Orchard, with some tweaks to allow for the possibilities of putting together actions that have different zero-knowledge proof states or different commitment tree routes. I will show it as 2 actions over here. I've mentioned in the slide that they are incomplete actions. So the way you can think of this is that it is this particular party's side of 2 Orchard ZSA actions, one to send 2 tokens of asset B and the other to receive 3 tokens of asset A. The design is such that when you combine it with the other party's swap order that matches, it will fill in the pieces to create complete actions to do both of these transfers. The swap order also contains authorization signatures so that it is clear it was issued by the appropriate party. And there is a new field added in this protocol, which is the time limit field. If there was no time limit, it would give the party performing the matching and posting on the blockchain what's basically a free option. That is, it would allow that party to wait indefinitely in the hopes of the exchange rate becoming more profitable for it, and then doing the swap in order to make some profit. Therefore, we have a time limit, which is expected to be a block number. Consensus will reject an action group that has a time limit that has already passed. So yeah, that was the simplified swap order overview. Next up is swap bundles, which is where we combine the swap orders. The swap bundle basically contains some header information. It contains the action groups from the specific swap orders that are being matched, and it has a binding signature. So when the swap orders are matched, the action groups from both these swap orders will exactly match the inputs and outputs. And this is what I'd hinted at earlier about the incomplete actions getting balanced during the matching process. I'd mentioned earlier about the commitment randomness being included in the swap order and it being useful for the matching process. So here's where it comes in. The binding signature needs to, as the name suggests, bind together all these different pieces in a way that it cannot be modified or cut and pasted in a different bundle. In normal Orchard, the transaction is created by a single party, so they know all the randomness and they use that to create the binding signature. Over here, though, we have randomness coming from two parties that needs to be combined in order to create the binding signature. We do this by providing the sum of the randomness of each party in their swap order and putting those values together to create the binding signature that we need. So yeah, if you look at the specification, you will see that the swap bundle structure actually looks like this. So I have highly simplified it to try and go to just the core of what is going on. A lot of the detail of why action groups are created and why they are needed and so on are explained in a lot more detail in the zip 228 and the rationale parts of that zip. We'd absolutely love for you to go over the spec and see what you think about it. So yeah, the great part about this design, as we said, is that it doesn't need any changes to the ZSA circuit. We will need to generate one proof per action group, so there will be multiple proofs in each swap bundle. There seem to be ways to aggregate Halo 2 proofs together, and so this is something that would be something good to do in the future. So this covers the updates that we were keen on giving from Kedit today. So thank you all so much for tuning in, and I think we have more time available for questions now. So the question is, do you have any recommendations for how swap coordination can be implemented such that the coordination itself does not involve a central party? If a central party is required, are there potential legal ramifications for that coordination action that would deter coordinators?
So indeed, for the swap mechanism to work, someone needs to aggregate the orders and then find the matching orders, match them, and submit them to the blockchain. So the simplest way to do it is to have a central party or multiple central parties that will receive orders from potential users, aggregate them and publish them to the blockchain. This is the simplest way. About the subject of decentralizing the matching process. So the first idea comes to mind is to create a decentralized network of matchers. So it's like a different network with a different set of incentives built on top of the existing Zcash tools and utilities. It is decentralized and incentivized separately from the Zcash network. This is the first thing that I can think of. The second thing is to go even further and to embed this functionality into the Zcash node. If the Zcash node is also also includes software to match potential swap orders. Basically, we can provide software that anyone can be the matcher and to earn fees as a result. But again, this comes with the price of an extra maintenance and extra effort on the Zcash side. These are just ideas, but these are the things that come to mind about decentralized matching.
So another question is, how do you think Zcash can attract more developers from other blockchain projects to collaborate and make alliances to push Zcash further, like NIM, Brave, etc.? So I think the major plus point of Zcash is that it has these strong privacy and security features. And since it has all these, it's like the original privacy coin in a sense. So a lot of these projects might be looking for things that enhance privacy, and highlighting that would be one way to draw interest. Probably more outreach, more networking at conferences, having grant projects available to do things like building bridges to these different networks. Those could open doors to more collaboration. And yeah, I don't know if any other points, Pablo?
So it's not really a technical question, but at least from the ZSA perspective, the ZSA does provide the tools to basically bridge any other asset from any other chain into the Zcash blockchain, which by itself would open a significant amount of opportunities for collaboration. This is from the technical perspective. Although currently to bridge an asset, a trusted bridge operator is required.
Yeah, I think a lot of the impetus would come also from the community, in that like when there's demand for things from the community, there's more chance of grants being sanctioned and more chance of other people, like people from other blockchains realizing that that's a good idea to do. So yeah, we'd love to hear more about people using ZSAs for all sorts of things once they get deployed. So one more question, is there anything that the Zcash Foundation and or the Electric Coin Company could do to support this work that isn't currently being done?
So the answer is no. We are in tight cooperation and coordination with both Zcash Foundation, technical teams, and ECC. I expect as we move closer to this project integration step, this collaboration will be even tighter, and we will have much more interaction with both of these excellent teams.
I think that's all the questions that were in the chat. So thank you all once again for listening in, and see you around Zcon.